Hi everyone. Let us move on to Unit 5, carboxylic acids. Thus far, what are the oxygen-containing molecules we've seen? We've seen alcohols, ethers, epoxides. We were able to oxidize alcohols to aldehydes and ketones. We do have one example of a carboxylic acid, and we saw that by oxidation of a primary alcohol. But there are other features to carboxylic acids that are important to know. And in this first video, I'm going to go over some of the properties. Oh, actually, first the nomenclature, and then some of the properties like hydrogen bonding and their acidity. And after that, in future videos, we'll take a look at more reactions with carboxylic acids. Okay, a carboxylic acid, as you probably know, is a molecule with a carboxyl group. And let's draw that. Let's put a couple of, whoops, what is all that? Let's put a couple of substituents. Let's put a chlorine actually here. Okay. Let's talk about nomenclature first. When you're numbering the carbon chain, okay, again, you are going to look for the longest carbon chain. You're going to include that carbon of the carboxyl group, and actually that will be carbon number 1. 2, 3, 4, 5, 6. I'm not going to write out all the rules. It's basically the same set of rules as before. Just know that carbon number 1 is automatically the carbon of the carboxyl. And therefore, the name of this molecule is going to be 2-chloro, 5-methyl, and instead of saying hexane, we are going to drop the E and add oic acid. And you don't have to put 1 because it's automatically number 1. So instead of hexane, drop the E and add oic space acid. Okay. Let me underline that for us. We added OIC space ACID. I should have mentioned this at the beginning. This is the carboxylic acid, but that's because you have a functional group called carboxyl. And this is in a separate unit because carboxyl groups have different reactivities than carbonyls. So they are different groups, or you could say they have different reactions than carbonyls, aldehydes and ketones. Carbonyls, XYL versus NYL. Okay. What is the simplest carboxylic acid? The simplest carboxylic acid has 1 carbon and looks like this. Instead of methane, you're going to call it methanoic acid. Now, carboxylic acids actually are very prevalent in a lot of consumer goods, whether they be ingredients in baked goods or even ingredients in shampoos and soaps. But many times when you read the ingredients list, they're not going to use IUPAC. They're going to use a common name, and the common name for this is formic acid. I typically ask my class to memorize all the common names for the first 6 carboxylic acids, all the way up to hexanoic acid. And I'm just going to go ahead and write that out for us. Methanoic acid, ethanoic acid, propanoic acid, Butanoic acid. Pentanoic acid. And hexanoic acid. The common names typically come or are derived from where this acid was first discovered. For instance, formic acid um, is, how do I want to say this? Oh boy, I'm not 100% sure. Uh, oh yeah, it is. I have it. The, my notes are in front of me. Latin for ant, and ant is formica. The irritant in an ant bite is formic acid, is methanoic acid. Ethanoic acid you know as acetic acid, vinegar, and the Latin is uh, acetum. Propanoic acid is similar to its common name. It's propionic acid. Butanoic acid is butyric acid. Pentanoic acid, oh, by the way, butyric acid, butter, or butyrum. So butter, I think when it spoils, uh, creates butanoic acid. The next is valeric acid from the plant uh, valerium. Valeric acid. And the last one is caproic acid. I'm not 100% sure about that derivation, although my notes say the Latin for goat. Your guess is as good as mine. Um, what part of the goat or where they found hexanoic acid in a goat? There's a mnemonic. There's a mnemonic where you could memorize the common names for the first 6 carboxylic acids. Again, hexanoic acid looks like this. Did not mean to write that. 1, 2, 3, 4, 5, 6, and OH. The mnemonic is frogs are polite, being very courteous. Frogs are polite, being very courteous, and you just count on your fingers. 1 carbon frogs are polite, being very courteous. 6 fingers, 6 carbons. The common names, again, like I said, you'll see these a lot. Just look around your home, uh, look at the ingredients of your maybe pantry items or in your bathroom. You'll see some of these. Now, there are also diacid common names, and the simplest diacid is 2 carbons. Okay, and so for 2 carbons, let me give you the IUPAC name. It's 2 carbons, so it's ethane dioic acid. Okay, you give the root, keep the E, add dioic space acid. Keep the E, dioic acid. This is oxalic. And we are going to go up to 7 carbons, meaning we're going to have 6 names. Ethane dioic. Next one is what? Propane dioic. And let's just draw that real quick. Okay, next is, I'm not going to draw them, butane dioic. I'm going to skip some. Butane dioic, pentane dioic, hexane dioic, heptane dioic. Just 7 carbons. Heptane dioic acid. Alright, so let me figure out if I could remember the common names. Oxalic acid, malonic acid, succinic acid, pentane dioic acid is glutaric acid. I'm going through my mnemonics. Adipic acid. So this is 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons. 7 carbons is uh-oh. Oh yeah, there it is. Pimelic acid. Oh my, such good apple pie. Oh my, such good apple pie. Okay. These also, I'm positive you'll be able to find these names in your pantry and also in your bathroom. Okay. Now, what's interesting about carboxylic acids is you can tell whether the ingredient is a salt of the carboxylic acid or is it the neutral carboxylic acid by looking at the suffix. For instance, let's go back to valeric acid. Valeric acid. Valeric acid looks like this. Got turned upside down. Valeric acid is that. If you want the IUPAC name, again, it's pentanoic acid, and that equals valeric acid. Naming is taking a little bit longer than I expected. If you deprotonate it to the O minus, this is a carboxylic acid. This is a carboxylic acid, but this is called a carboxylate. And pentanoic acid becomes pentanoate. So you get rid of the ic acid and you add 8. And you want to do the same for valeric acid, you could call it valerate. You know this, you've seen this before, because you've heard most likely of glutamate, malonate. How about pyruvate, right? Pyruvate is a carboxylate. And what carboxylic acid did pyruvate come from? Pyruvic acid. Lactate, lactic acid, etc. Okay. Now there is one more naming thing that I want to talk about. This is the IUPAC name, 2-chloro-5-methylhexanoic acid. But if I wanted to use the common name, my root would be what? My root would be caproic acid down here, caproic acid. Let me show you, not only do we change the root to the common root, oh, did I say valeric? Oh, caproic. Not only do we change hexanoic acid to caproic acid, we actually change the numbering system. And we go to Greek letters. And I think, well, this is the second to last thing for nomenclature that I want to talk about. Let me draw you the alpha, beta, gamma, delta. Okay, let me draw you that molecule again. And we had a chloro group at carbon number 2. And we had actually a methyl group on carbon number 1, 2, 3, 4, 5. Therefore, the name for this molecule was 2,chloro-5-methyl-hexanoic acid. Okay, let's use our mnemonic. Frogs are polite, being very courteous. That gets me up to 6. So C is caproic acid. I'm going to put that here before I forget it. Caproic acid. Now, we don't use numbers when we go to the common name. We use Greek lettering, and this is tricky. Okay, just be careful. This is the alpha carbon now. It's tricky because, if this was just a hydroxyl group like this, we could do beta hydrogen elimination. This is actually the beta. The thing is, since you can't have any substituents on this carbon, we're going to call the carbon next to it and start the Greek lettering there with alpha. Just be careful. With alcohols, again, the carbon that's attached to the oxygen, that's the alpha carbon. But for aldehydes, ketones, carboxylic acids, it's actually the carbon next to the C double bond oxygen that's alpha. And the order goes alpha, beta, gamma, delta. And I think the next one's epsilon, but it'll be unlikely you go that far. Alpha, chloro. You see how this is changing? Delta, methyl. There should not be a space there. No space. Okay. IUPAC, common. For my class, you would be expected to know how to name a carboxylic acid both ways. The only other carboxylic acid that I want to give you the name for is the one with a benzene ring. And that is benzoic acid. Okay. That's it. Naming is pretty simple except for all of these common names that you are expected to memorize. Is there anything else I want to talk about? I talked about the when it becomes an anion, when you deprotonate the carboxylic acid. I think we're good with this. I want to next discuss hydrogen bonding, and actually that's going to follow closely by boiling point or melting point. Because carboxylic acids, they are set up perfectly to have actually what's called a dimer complex. Dimer meaning 2. And let me just use benzoic acid. Hopefully I can draw this properly. You remember hydrogen bonding? Hydrogen bonding is when two molecules associate with each other via hydrogen, but that hydrogen has to be connected covalently to a oxygen, nitrogen, or fluorine, and then it has to have that partial hydrogen bond to a oxygen, nitrogen, or fluorine. All right, so let me show you that. We're going to draw benzoic acid like this, and I'm trying to keep my bond angles as precise as possible because now I want, I hope I could do this. I want an H here, O there, O there, and then benzene. Your hydrogen bonding is right here, and each benzoic acid acts as the donor and the acceptor. Like for instance, the blue benzoic acid, there's a hydrogen bond donor here, right there, but also there's a hydrogen bond acceptor. This is called dimerization, or the complex itself is called a dimer, a carboxylic acid dimer, and it's pretty strong. It's not covalent strong, but when you have benzoic acid, even in the solid state, you'll have these hydrogen bonds. The thing is, we know that if you double or if you increase the molecular weight, with all things being equal, the boiling point or the melting point goes up. Let me write that for you. Boiling point or melting point goes up. They're harder to separate, and they need more heat to separate when molecular weight increases. And all things are equal. Okay, so we can't have, there's a possibility that a very light molecular weight molecule could have a higher melting point if it has a lot of hydrogen bonding. So with all things being equal, yes, then when you increase the molecular weight, the boiling point and the melting point go up. So I need to write that disclaimer. Because what's happening here is that this molecule, the benzoic acid, is actually acting like a molecule twice its size, which increases its boiling point and melting point. So let me give you a trend, and we could look at these molecules in the context of each other. And yeah, I am going to try to keep the molecular weights fairly close, I hope. Let me give us another carbon. Okay, so there's a carboxylic acid. It's going to have a higher melting point or boiling point. Just depends whether it's a solid or liquid, but I think this is going to be actually a, I have to double check. I'm going to say it's a, well, this is tricky. Yeah, we'll do melting point, right? If we have a molecule that's a liquid, then we have to drop the temperature and freeze it to get to the melting point. Because the other molecule, the next molecule I want to compare is this molecule here, an alcohol. Okay, I'm trying to have the right number of atoms so they're close in molecular weight. So I don't have an oxygen up here. I replace it with a carbon or a CH3 group. Approximately the same weight, but with the molecular weights being close together, the one that has a carboxyl group has a higher melting point than the alcohol. Okay. Then we have hydrogen bonding of, it's called an amine, but the hydrogen bonding of OH groups are stronger than the hydrogen bonding of NH. Let me write that down. H bonding strong, H bonding weaker. Okay. This one makes a dimer through H bonding. And again, it's acting like it's double the molecular weight, which would definitely push it above the melting point of this molecule here, or any other molecule that we're going to talk about. Next is sulfur. It's not hydrogen bonding. It's just dipole-dipole. Okay. What else? We talked about aldehydes and ketones. They're next. And how do I want to draw this? Oh, man. The methyl group shifted. Let's draw the ketone like this, and the aldehyde like this. Okay, that's next. These have strong dipole-dipoles, not as strong as an SH. Right, you can almost think of SH as somewhere in between hydrogen bonding and dipole-dipole, but technically it's not hydrogen bonding. Okay. Let me zoom out. Next is maybe something that doesn't have as strong as a dipole, ethers. And let me give us this one here. That's analogous to the molecular weight. Ethers. And then something that has no dipole bonds, alkanes. That is your trend in terms of boiling point slash melting point. Okay. Next is acidity, and we're going to go through this a little bit quickly. If you have a carboxylic acid, well, no. Let's start out with an oxygen-containing molecule that we've talked about already, the alcohols. Let's call this acidity. And the alcohol I want to use is ethanol. Ethanol has a pKa of 15.9. Okay. And if we look at the carboxylic acid, it drops. And this particular carboxylic acid is 4.6, 4.8. And why is that? Because when we deprotonate a carboxylic acid, we have resonance. Okay. And the resonance is here. So we could say that the anion is resonance stabilized, and that's why it's okay to have a negative charge on oxygen here. But here it's not so good because it's localized. So resonance delocalization. We've seen the trick before where you replace hydrogens with fluorines, and this is a very popular type of carboxylic acid. This is called trifluoroacetic acid, 0.2. Trifluoroacetic acid. Again, when you deprotonate this to make the anion, the fluorines now are stabilizing the anion via induction. Did we talk about induction before? We definitely talked about induction when we looked at alcohols where we replace the hydrogens with fluorines as well. Now resonance is a better stabilizer, but this molecule has both resonance and induction. Resonance and induction. Nothing too special with benzoic acid. Okay, there's really no extra stabilization, so this is around 4.2 that we had for just a regular carboxylic acid. And the last one is a diacid. I want to show you that when you have a diacid, remember what the name of this is, the common name? O has 2 carbons, Mi has 3, such is 4. Such, good apple pie, but such stands for succinic. This has to have 2 pKa's. This is very common in biology, where you have molecules, biomolecules that have multiple carboxyl groups, and as you start plucking off protons, it gets less and less acidic for the next carboxyl group. pKa 1 is 4.2. Okay, that was predictable. It's just a normal carboxylic acid. But once we have that negative charge, for instance, on the left, it's actually less likely to remove a second proton to make it a dianion, because we don't want molecules that are typically multi-charged. And we see that in the pK2, it's not that much higher, but it is higher, it's 5.6. The way when you think about pKa's, I don't know if we ever discussed this, but for instance, 4.8. If the pKa is 4.8, that means at pH 4.8, you could say that half of the molecules are deprotonated. That's how you use, in practice, this pK and pH, the relationship. Half molecules are deprotonated. If you want to get more of the molecules deprotonated, you make it even more basic. You raise the pH to 6, to 7. So at physiological pH, 7-ish, 7.4, there's almost exclusively basic, right? Yeah, exclusively this is all deprotonated. Um, all right, that's all I want to talk about in terms of an introduction to carboxylic acids. The next video most likely is going to be a review of how we make carboxylic acids, and we do have a couple ways to do that already, and then a new material where we use carboxylic acids to make some other classes of molecules that we have not seen yet.